Hey, hello, how are you? Long time, yeah, 12, eh? Hilary and then George, Eugenia, Joelia. I hope you guys are fine, eh? Plus the rest will view the video, of course. But I was looking at some numbers about expectations and then variance, and I discovered there is a proof that you guys might not be able to crack down for yourselves. And I believe after I've done the proof, you can do the rest of the numbers about expectation and variance. I hope you're doing good and you're reading. Now, in year 12, what you're expected to look about is what we call the probability discrete random variables. I'll use a pen, not a marker, in this video. Like, there's what we call the probability. There's what we call the probability discrete. I want you to look at that book that I shared with you guys, and then you do those numbers, or you make your own revision, please. Some other people call it the PDF. Yeah. So some people call it the PDF. Then there's what we call the CDF that we shall look at under when we get to year 13. So now here basically. So here basically there's what we call the expectation that you're going to look at, expectation and variance. I want you to play the video slowly until you've understood what we are doing. Here you told me numbers are tight, so I hope this will help you try to get something. So there's what we call the EX. So when you start with, so basically this is what we are looking at. It is about page 114. Let me check on this computer and see where it is. Page 100, I think page 114, 100. It's okay. Can take my time as you organize your books also. It is page 115. And then we shall do that example there, and then I'll let you guys continue with the hustle that side. So there's what we call the EX. When you look at after there's what we call the EX, sorry about my environment, equal to mu. I think that's okay. Mu, we agreed the expectation of x is equal to mean. This is what means the expectation of a random number, x, is equal to the mu, which is the mean. So when you get the expectation of a number, it should give you what we call a mu. And then another one tells you that the variance of x is equal to a sigma squared. So it's okay. But now when you start with expectation, I want to look at those formulas for you. I'll try to break them down, and for any questions you can reach me through Mr. Robert, or if at all you have my number you can text me, we see. So yeah, the number says the expectation of x is equal to a mu. And now this is equal, this is one of the formulas, it's okay. Or the expectation of x can equal to the summation of a random variable r times the f of x, yeah. So which is just basically the probability of x equals to r. When you look at that book, it is there. And I want you to take something that I've discovered that maybe most of you could be confused about. Sometimes they might not give you r random variables, and they'll give you x random what variables. It will still be the same thing as we have in this is the summation of x times the probability of x equals to a small x. Now it is not a capital X. So some other people or some other books will bring this p of x equals to r, and this will equal to the function of x. In there now the general formula might be the summation of x times the f of x when they ask you to get the expectation of x. These numbers, if at all you are reading, you've seen where these formulas are used. So there is what we call the summation of x times the f of what? X. This can be a formula, assuming we are using x's, or this can be a formula also. Basing on the number that is done as an example, this is what they used. So we can either use this or shall use this, depending to whatever you want to do. And from there, the hard proof that I saw was the proof for Oh, then there is something that continues. And another person, so this is 1. These are different formula. This is formula 2. This is formula 1. Then another one, 3. I hope you can still see it. It says the expectation of x can also equal to the summation of r with a subscript r somewhere. On the probability, this is the same as this one above. If at all we substitute this r with the x, it shall still be our r. So some other books, especially to you guys who continue with math, you find a book that will give you the summation of x times the f, but with just a simple subscript of x. It can also be still work, but I want you to basically take this one above and maybe also consider this one, depending to what shall come when I proceed and look at variance. I'm trying to break this down, and I'll do the number there, and we'll wish you guys success. And as I try to continue looking at what could be hard again. So there is what we call the variance. I'm just trying to break down the formulas for you because I discovered the formulas are slightly hard. So now the variance of x, this is the same as the val of x. And then they say in the book that the value of x can be written as the sigma squared. If you're lucky and you've continued to read up to the normal curve of using the phi of the z curves and stuff, you've seen this, that some of them might give you the binomial distribution of this, and then they want you to read it from the binomial tables. I don't know if you've read to that extent, but that work is there for you. So this one says you can have the sigma squared equaling to the expectation when you have this into some other curly bracket of x minus mu squared. What does this give you? Then they're saying this can be the formula. However, of course, there's no way you can apply such a formula. You have to break it down. In the book, they gave you this, then they gave you, when you look at the part of O, sigma squared is equal to the expectation of x squared minus mu squared. How does the mu squared come about? That's what I'm going to break down for you. I'm just going to expand this, and then we shall see about it all. Hilary, I hope you're following. And then from there we shall have e into x squared minus 2 mu. I'm just expanding this. I think the teacher of paper 1 did for the Pascal's triangle. So this will be my mu x plus mu squared. Look back to your expansion of such a bracket. So this one comes back and this one comes back as a square, then they have a difference. So now you can also look at the one of the expansion of x plus maybe a y squared. It is now the opposite of this here. This one too, now for this case, this one will be a positive 2yx. It is just still the same thing. So I'm taking this to be my x and this is my y. Just that this time around the y is a negative. So when we have this, what comes next? We shall now enter. I'm writing it down that you can follow. So you enter the e, this e here, into the brackets. Yeah. So when we enter the e into the bracket, what comes out of it is now your e into your x squared. Now I want you to see that this expectation sign will not affect a constant. Expectation of a constant will equal to the very constant. It will only affect the random variables of x. That is what is not explained in the book, that I thought that some of you might not be able to explain. So this is basically my e of what? X. Once we put the expectation on the mu squared comes back as a mu squared. Like the expectation of constant mu squared, it's still just the mu squared. It won't be affected. That is not explained in the book. So if I told you you're wise enough, you would ask how does it still remain with just a mu squared when you take off the e bracket and stuff. So but somewhere we are done something to do with the expectation of x, and what to do did we get? We got the expectation of x equal to a mu. this is from the upper one when we say the E of x is equal to a mu, or this is equal to the summation of x, f of x. It is okay. But now I'm only considering this one for the case of the proof. I'm not taking this other formula. I hope now you can appreciate why they used both. So when you have that, I'll have my E into my x squared. You feel free to pose any question later on. So this is a 2u times a u, because I'm now substituting this one for just a mu, not even a u, but it's called a mu. Those are Latin letters, like the Greek letters. So in that we shall have a 2 mu times our ex, which is now a mu, plus a mu what? Squared. So I'll still have my expectation of x squared minus a mu times a mu, it is a 2 mu squared plus a mu what? Squared. And now this means we shall have our E of x squared. So this is plus, so 1, this becomes a mu what? Squared. So when you look at the notes, that is the next answer that they give you. I hope you can see it, you guys. The next answer that you are given when you're looking at those numbers. In that now they will tell you that your summation, your sigma squared, which is your variance, is equal to your E of x squared minus mu squared. This can be a formula. So when you're given x squared and you have a mu, you can square it and then you have variance. That is okay, I think. And now I want to look at the last one. The video will be slightly lengthy, but it's okay, you have to bear with me. Let's make it as a class here, make life slightly easy for you. So when you proceed down, there's something that they say, the next formula says, and then your variance of x equals to the summation, good, the summation, let me look at the summation, this is the summation sign, of r squared, the summation of r squared, this computer shouldn't freeze now, the summation of the summation of r squared, the probability of r, this is just the probability of r with the subscript r down minus something like this. Now, so if I told you you've read it, the next question you'll have to yourself, how does that come about? But if you're keen, when you look at what I've done here, it is an extended proof of this. If I told you a curve wasn't enough, it is an extended proof of this. So I'm going to proceed with this. Since I have a mu here, so my mu is basically, my mu is my ex equals to a mu. So I'm going to put them back and see how that can easily be decomposed, and then we shall try to put in what the function of x back and see if it can create our variable. And from there we shall do one number and see whether you can try to apply it, and I believe life will not be so hard. And that will be the end of the discrete random variables, and then I'll do one more number for probabilities in case there is a way. So we shall have this as a variance. I'm going to prove this if you're following your notes, George, on the book I gave you of your AS statistics. So we shall have the val of x. The proof is not needed when you're doing a paper, but if you don't understand the proof, you won't be able to do these numbers. That's what I've discovered. And what formula will you use? So I'll do them for you. So val of x can be given as our ex squared minus, so instead of my mu, I'll come and use the expectation, but recall that expectation is squared here, yeah, because it is a mu squared, but I cannot just square this x. It is the whole of the ex that has to be squared. So some other person might just have it as my e of x squared minus the e of x. It is okay. This can also be much more better for you other than this, but mathematically this is much more approved. So from there, how do we start to decompose this? Now recall, basically what I'm trying to look at now, this is formula 2, the other one was formula 1. this expectation of a squared, it doesn't really create much. You just have to, it goes to what we call a summation sign of our x random variable squared times the f of x. I hope you guys can get that, because here we had the expectation of x, and this was equal to my summation of my x times the f of x. Now in math, when you have the expectation of a variable squared, it is the same as that variable squared times the function of x, or the probability of x, depending to what you are doing down. Now this one, we know very well, we've already done the expectation of x as equaling to the summation of our error. So here too we can have it as an error and not an x. Basing, we've said we can interchange the error for the x. So my final answer, so this one can be, now let me first use an x times the f of x, and this is a square that is within the formula. But when we use the formula instead of the x and we use the error, so the formula has it as a summation of error squared times the probability with the suffix error minus the summation, which is in enclosed brackets, the summation of error times with the suffix error, but this is squared. I hope this is easy to understand. You can play the video more than once. We can interchange these ones for each, depending, yeah, and from there that will be, oh, those will be the formulas. Hope that's okay with you people. In that when you proceed, when you see after these formulas, they'll tell you these formulas can also be written. So the formulas can also be written as the summation, as the expectation of x equals to the summation of xp. This tells you what I've done here, meaning my side work aside. So my p is the same as the f of x in this case, or the probability of x. I think you guys can easily get this as my p, x equals to r. That is the same thing. And then when you have so this is one of the formulas, and then later on your value of x can also equal to the summation of x squared p minus your expectation of x squared. So when you look at that number below, I don't want you to get confused. That number starts from page 144. So they've given you the error. So this error can be the x, and then later on they've given the probability of getting an error out of the number of samples of cars. And then you start just doing. Then you look at the formula, and then you start creating the table. I hope you guys can see it. So you look at the error, then you start creating the table. Let me try to show it to you easily, maybe. Let me try. So that's the number I'm saying. The error here is basically given. It is from page 144, and now this p error is the probability of getting that type of a vehicle. So when you use them, what you're seeing here above, these ones are basically to fill in what is needed in the table, yeah, but they are getting them from the formulas. Guys, I wish you the best and good luck. Thank you.